The genius, Michael Faraday, was born into very modest circumstances which afforded him little opportunity for formal education. To improve himself, he attended public scientific lectures at the Royal Institution in London. This exposure to the giants of science of the late 18th and early 19th centuries led him to the formulation of the concept of electric field. In 1789, Charles Augustin Coulomb confirmed what the scientific community had suspected for years. Coulomb finally demonstrated that the electric force F is inversely proportional to the square of the distance r between the charges Q1 and Q2. As elegant as Coulomb's experiment was, the concept, the idea of the inverse square relation, had been a major scientific notion for some time. A century earlier, in fact, Isaac Newton's theory stated that the fall of an apple and the orbit of the moon were both consequences of the same basic laws. And one of those laws, the law of universal gravitation, states that any two masses attract each other with a force inversely proportional to the square of the distance between them. In England, the law of gravitation became the law of the land. And by the 19th century, with the law of gravitation firmly established, Newton's followers had discovered that electricity and magnetism obey similar laws. In all of them, the force decreases with the square of the distance. The similarity is amazing. The question is, why? The essence of the inverse square law can be seen in the concept of flux, the Latin word meaning flow. Light flows out from the sun equally in all directions. As it spreads out, getting farther from the sun, its intensity decreases. But imagine a sphere enclosing the sun. All the light would pass through the sphere, no matter what its distance from the sun. And the area of a sphere grows as the square of its radius. So the amount of light energy per unit area decreases as the square of the distance. The inverse square law wasn't the only provocative idea to which the young chemist Faraday was exposed. Sparked by curiosity about various electrical and magnetic phenomena, Faraday set aside his work in chemistry to study electric and magnetic forces. He began with a number of assumptions. At each point in space around an electric charge, a small test charge, held by the hand here, experiences a force, shown by the arrow. If it's due to only one charge, the pattern of forces detected by the test charge is simple. The pattern's more complex for two opposite charges. Or for two charges of the same sign. And more complex still, for more complicated arrangements. But in any case, here's the point. Even if the test charge isn't there to feel it, the pattern of forces can be imagined to exist everywhere in space. This is the essence of the idea of the field. And although Faraday only imagined it, the field can also be expressed mathematically. force that acts on a test charge at each point in space is equal to the test charge Q times a quantity due only to the other charges. That quantity is the electric field. Faraday never arrived at that definition of the electric field. But by seeing both electric and magnetic phenomena as forces in space, he managed to see further than his peers. As a researcher, he saw deeper and deeper into the invisible forces of space. To Faraday, the 1/r² force between electric charges suggested that the force must be applied by something radiating outward from charges, something which, like light from the sun, never stops and never ends in space. As Faraday imagined it, this something would be lines or tubes, each one capable of applying a force to any charge in its path. These lines of force would begin only on positive charges, indicated here in red, and end only on negative ones, indicated in blue. And they would flow smoothly through space, never crossing or tangling. No matter the configuration, the charges would have a characteristic pattern of lines. The force they applied would be strong near the charges where the lines are crowded together, as indicated by the larger force arrow on the test charge, and weak far from the charges where the lines are farther apart. The ability to apply a force resides at each point in space, and the force arises from the density of lines, regardless of the location of the charges that create them. Even without such space-age graphics, this is how Faraday pictured the electric field. And it still seems the most graphic way to visualize one. Combining Coulomb's law with Faraday's notion of electric field reveals a number of amazing facts about nature. For example, watch what happens inside a conductor where a lattice of positive ions is neutralized by mobile and constantly moving electrons. An electric field passing through a conductor forces the electrons to flow until they pile up at the surface, repelling the motion of further electrons. But that means the electric field inside any conductor becomes equal to zero when electrostatic equilibrium is established. But even though there's no field inside, there can be charge at the surface. And no matter what's outside, the surface charge makes the field inside equal to zero. And since all the action's at the surface, a metal box of any sort, even a flimsy screen-covered cage, can keep out an electric field. That fact can be demonstrated with this device, a gold leaf electroscope. Notice how it responds to the field of an electric charge. Notice, too, that even when an electroscope's inside the cage, it reacts in the same fashion. However, when the box is enclosed, an electric field can't enter to disturb the gold leaf. Any metal box can do it. And to this day, any metal box that does do it is called a Faraday cage. Of course, not every Faraday cage was designed to protect its contents from electric fields. The steel girders of a bridge or the scaffolding of a tunnel probably couldn't care less about keeping electric fields at bay. But they do a pretty effective job of it nonetheless. Why? Because radio waves are a kind of disturbance in the electric field. And because whether it's a bridge, a tunnel, or merely the enclosed container that its name implies, a Faraday cage isn't a great place to get good reception. Outside again, the reception's fine. Michael Faraday's background in mathematics was limited. James Clerk Maxwell transformed Faraday's picture of lines of force into a sophisticated mathematical description of the electric field. But in its development, Faraday's lines of force provided a kind of mental scaffolding, a structure that was constructed before the real edifice was built. Responding to a letter from Faraday, Maxwell wrote, "You are the first person in whom the idea of bodies acting at a distance has arisen as a principle to be actually believed in. Nothing is clearer than your descriptions. You seem to see the lines of force curving round obstacles and driving plumb at conductors, and swerving towards certain directions in crystals, and carrying with them everywhere the same amount of attractive power spread wider or denser as the lines widen or contract." And thinking of gravity as well as electricity, Maxwell concluded, "Your lines of force can weave a web across the sky and lead the stars in their courses."